Okay. Hello, everybody, and hello, everyone who's joining us for the recording. So our topic today is improper integrals, which is section 1.5 of the lecture notes, and the last section in the first chapter on integration techniques. So let me highlight that we're talking about section 1.5 of the lecture notes, which is on improper integrals. So just before we launch into the kind of examples and detailed notes on this topic, I'd like to try to explain a little bit what the theme is, because it is something that kind of will be a bridge for us between the integration topic that we've been talking about and the properties of the real numbers that we're going to be talking about in the future. And one of the things that we'll be interested in as this course proceeds is the concept of infinity and how it's dealt with in mathematics, and how we sort of come to terms with working with infinity and kind of dealing with different magnitudes of infinity and this sort of thing, which is relatively modern in the history of maths, and which is, I think, in my opinion anyway, quite an interesting theme. So this topic of improper integrals kind of starts to touch on that. So let me say what it means. So in our discussions about integration, as we all know, we've been talking about computing definite integrals where you have some left and right hand endpoints A and B, and you've got some function in mind, and you look at the graph of that function. And it's something that we can handle maybe, and we care about using techniques of calculus to compute things like areas under curves. And so we know that this blue area in this picture would be the integral from a to b of f of x dx. And if we're able to find an antiderivative for f of x, then we can calculate that as a number, which is really nice. And we've been doing plenty of that. Okay, the question that we look at for the term improper integrals refers to something related to that. And basically asks, supposing we had some function. So this is this interval a to b. This is like a bounded interval from a to b. We'll have a formal definition of bounded later. But what it means is, it's an interval of fixed length. It is a left-hand endpoint and a right-hand endpoint, and we know what they are. We know the distance between them, for example. Suppose we wanted to compute an area like that over an infinite region of the horizontal axis, that is right, the x-axis. Okay, does that make any sense? So what do we mean? Okay, well, for example, supposing you had some function in mind, and let's just take as an example the function y equals 1 over x, or f of x equals 1 over x. So it looks like this, as we know. It's not supposed to have that disturbance there. But let's just suppose that this is the graph of the function y equals 1 over x. Or this is the graph y equals 1 over x. Okay, so for example, I'll cover up that mess by writing this. So this is the point, for example, 1, 2. When x equals 2, y would be 1/2. So this is the point 2, 1/2, and so on. And the graph gets nearer and nearer to the x-axis as we travel further out. So let's say that you wanted to calculate, let's say you wanted to talk about some region like this. The region enclosed under the graph y equals 1 over x, just to the right of 1. So here's 2, here's 3, and the height of the graph at 3 is 1/3, and so on. And as we travel further along, the graph, which is this black line, gets nearer and nearer to the x-axis. And we can certainly talk about that region. So it's a region that's kind of infinite in width, and its height is finite at every step, but its height is shrinking as you travel out to the right. So, could we talk about the area of that red region? So, on the one hand, maybe, well, it makes no sense, because when we're talking about a region that's like infinitely long, and if you were to kind of try to approximate it as a rectangle, you'd want to multiply its length by its height or something like that. Well, you can't do it because its length is infinite and its height is varying, whatever. But it's not, it's not something that you can deal with by trying to use the ordinary methods of calculating areas of rectangles or anything like that. So, question is, can we think about the area of this red region? So it would be the area enclosed between the graph y equals 1 over x and the x-axis to the right of x equals 1. So it looks like an ordinary definite integral. And we would indeed write it as, so it's an example of what they call an improper integral. And you'd write it as integral from 1 to infinity 1 over x dx. Okay, but because so the infinity just replaces the upper limit, meaning we're integrating all the way to the right of 1. Okay, so of course you can write that down. You can write anything down. It doesn't necessarily mean that it makes sense. The question is, can we calculate this thing? Is it possible to conceive of that area as actually being a number? Or is it infinite? Is it something that we can measure? Is it something that we can make sense of at all? Okay, this is what we're going to talk about in this section. And I suppose a couple of remarks that one could make. I'll just insert another page here. This is all very vague, but we're going to make it a bit more precise. If you were looking at something like if you were to take, for example, the function the graph y equals 1, something like that, and you were to do the same thing, think about all the area. So it's a constant. I mean, it's the graph of the constant function f of x equals 1. And if you were to talk about like trying to integrate that everywhere, the whole way to the right of 1, but then you'd be talking about a rectangle that has like infinite length and has height 1 the whole way along. And that certainly that area is certainly infinite. It's just, there's no way that you could expect it to be a finite number, because it's sort of like, it's the infinite length multiplied by 1. So this red region would be where we understand that it kind of extends infinitely to the right of the picture. That would be the integral from 1 to infinity of 1 dx. Okay, and I think that again, it would be an improper integral. We'll define this precisely in a minute. This is certainly an infinite area. We could think of it, if we liked, if you wanted to sort of make some kind of argument to persuade some skeptical person that this area is definitely infinite, you could say, well, if you were just to take the area from 1 to 2, well, that's a square of area 1, and then you've got the square from 2 to 3, which is another square of area 1, and the whole thing is it's a collection of squares of area 1, and there are infinitely many of them. So the area is certainly infinite. It's not any number that we can put a value on. Okay, but if you take something where the graph of the function is approaching 0 as you travel out to the right, then I think about like the area accumulation functions that we had when we were talking about the fundamental theorem of calculus a couple of weeks ago. Then the question is kind of different, because if you take, for example, we looked at 1 over x, but if you take the function y equals 1 over x squared, so again, the graph of it looks, in the positive side of the picture at least, quite like the graph of 1 over x, but it's even lower in a way. So if this is the graph of y equals 1 over x squared, then, so for example, like when x is 1, x squared is 1, so the point whose coordinates are 1, 1 is on that picture. If x is 2, though, then 1 over x squared is 1/4. So this would be the point 2, 1/4 with those coordinates. If x is 3, then 1 over x squared is 1 over 3 squared, which is 1/9. So the point whose coordinates are 3, 1/9 is on that graph, and so on. Of course, we can write down more of them if we want to. But I'm certainly, as x heads out towards plus infinity, 1 over x squared is 1 over a number that's growing fairly rapidly, so it's getting towards 0 quite rapidly. And so, here, if we were to ask, well, what about the region here enclosed between that graph and the x-axis? And think about sort of trying to measure up this area as if you start at 1 and travel out to the right from 1. You're accumulating area all the time, and you're going to travel infinitely far along the axis. But the further you travel out, the less area you're accumulating. So as you go further out in the positive direction, the height of this graph is approaching 0, and you're kind of getting less and less area all the time. So could it be that somehow the rate at which you're accumulating area is decreasing fast enough that somehow the total area could actually be finite, even though the region has sort of like an infinite base and it has a rapidly decreasing height as you travel out So, is it possible that somehow the rate at which the values of the function 1 over x squared are approaching 0 is fast enough that it somehow kind of counterbalances the fact that the length of the region is infinite? Could you actually end up with a finite area that you could actually calculate and that you could actually put a number on? And what would that even mean? But, it's a good question. Is this the same thing as Gabriel's horn? It's related. And actually, Gabriel's horn is the thing that we should look at. I don't think it's quite the same thing, but it relates to the same kind of questions. And we're going to be looking at more of those sorts of questions as we proceed. So certainly, it's related, and it's a question that we can ask. And I suppose so these questions are part of they're sort of almost at the intersection of mathematics and philosophy in a sense. Are these things that we can deal with? Do the tools of mathematics allow us to deal with them? And the answer is to an extent. And in particular, the tools of integration that we've been developing over the last few weeks enable us to deal with this particular question, which is what we're going to do in today's lecture. So one remark about 1 over x squared compared to 1 over x, I'm really, this picture is already quite bad, so I'm going to actually draw another one. Sorry for all the pictures. But 1 over x is a function that's decreasing when x is positive, of course. So let's say this is the graph y equals 1 over x. And the graph y equals 1 over x squared, which is supposed to be the one in this picture here. The one picture on the left here. 1 over x squared is decreasing even faster than 1 over x is. Okay, both of them pass through the point 1, 1, because both 1 over x and 1 over x squared are equal to 1 when x is equal to 1. And 1 over x squared, when x is 1 or more, x squared is greater than x. So the graph 1 over x squared lies below the graph 1 over x. And when x is less than 1, then x squared is less than x and 1 over x is higher. So if you cared about like the integral to the right of 1, you'd be starting at this point. And a remark is just that this green graph, which is the graph 1 over x squared, it sits, both of them have the x-axis at the horizontal asymptote on the positive side, but the graph of 1 equals x squared sits below the graph of 1 over x. So its values are approaching 0 even faster than the values of 1 over x are. And the reason I bring this up is just because it might have a bearing on the question of whether either or both of these graphs encloses a finite or an infinite area to the right of 1. So we're going to be able to answer this question. And so first I'm going to suggest that we just do we haven't done a poll for a while. So I'm going to throw it open. This is not really asking you to give this is asking you for sort of a immediate reaction rather than an analysis of anything. So anybody have a question before we open this poll? Okay, let me just throw out this question and see what you think. So do you think the area enclosed by the graph y equals 1 over x between 1 and infinity is finite or infinite, or we can't decide? All of which I think are very plausible answers. And what about 1 over x squared between 1 and infinity? Could these questions have different answers? Or would we expect them to have the same answer? So I'll leave it open for a few minutes. We have 100 people participating in this meeting, so I'll wait until we've had a chance to vote. Maybe I'll pause the recording for a second so that anybody who's watching it can choose to wait and think about this or not, and just share the results. So hopefully you can see that. So yeah, so for the graph y equals 1 over x, which is sort of like the higher of the two on that region between 1 and infinity. So yeah, we have a tight balance. So 49% of us voted that the area of that region is infinite. 41% of us said it's finite, and 10% of us or so said we can't determine that. I think all of these questions are absolutely plausible, all of these potential answers. And actually, a slightly different vote for the other one. The other one, the finite was the winner. 48% of us said that area is finite for 1 over x squared. 41% of us said it's infinite, and 12% of us said it is not determinable. So let's see if we can add some analysis to this sort of gut feeling and give a suggestion about how we might attack these questions. So yeah, so great. So it turns out that these questions don't have the same answer, which is remarkable to me, and I think it's fascinating. One of the reasons that there's so much to say about the real numbers. So let me stop sharing the poll results there and kind of have a look at the concepts as such that we're going to look at. So here's a bit of a more technical description of what we just talked about. So if we have a continuous function that has the property that it's, sorry, yeah, let me just close the poll. Can you see the slides again? If you can't, somebody complain in the chat. I'll assume that you can't otherwise. So suppose f of x is a continuous function that has this property that as x heads towards infinity, the limit of f of x is 0. And that just means, you know, that means that the graph of f of x looks somehow, we don't know what it looks like sort of near to the y-axis, but as we head out to infinity, it has the x-axis as a horizontal asymptote. So that basically the area that you're accumulating as you head further out is approaching 0. Because if that's not true, then there's certainly no way that we can make sense of the area of some region enclosed underneath it as we head out towards infinity as some kind of a, you know, finite area. So that's kind of a condition that we need to consider this question. And so, for example, f of x equals e to the minus x, 1 over x squared, 1 over x, 1 over the square root of x, all these things have that property. So then we can consider the total area between the graph of the function and the x-axis to the right of, for example, x equals 1 or some other fixed value of x that we care about. And the area, as we said, is denoted this way. So it's just like a definite integral, except that it's not a definite integral because it's got this sort of infinite region over which you're integrating. But it's not an indefinite integral either, because we're not talking about the general antiderivative. We're talking about the sort of conceptual area of some region. And the reason I use the word conceptual is because we haven't figured out yet if we can actually calculate these areas. Okay, so for a given function, you know, looking at it, you have this sort of infinite width and this shrinking height. And, you know, the question is whether the shrinking height could somehow compensate for the infinite width and whether you could actually calculate the area of such a region. Okay, and so if the area, our first question is, you know, can we determine whether this area is finite or infinite? And just a bit of lingo. If it's infinite and we can establish that, we say that the improper integral diverges or it's divergent. And if it's finite, which will sometimes happen, we'll say that it's convergent. And so our question really is, you know, what can we do with these areas? Can we do anything with them? And fortunately, the techniques of calculus that we've studied actually do enable us to do something with them, and also our knowledge about limits. So what you do with an integral like this, and again, this is sort of the formal side of the picture, the technical language for describing the situation. So if we've got some function f of x, and let's just assume that the function is something relatively manageable in that we can at least calculate an antiderivative for it, and you're trying to think about the area to the right of some fixed point a or 1 or whatever. Okay, so we can't really calculate the integral from a to infinity of f of x, but for some point b to the right of x, we can, in principle, take the limit from a to b of f of x. And that will be some expression involving b. And we can, in principle, or in practice, hopefully, take a limit of that as b goes to infinity. And that's kind of a practical approach that we can bring to this problem. You know, we can look at a picture of this region and, you know, reflect on whether we think its area might be finite or not. But we can, in a more practical sense, we can actually calculate a definite integral from a to some b to the right of a of our function f. Hopefully, we plug in the a and the b, we get an expression. And we can take a limit of that as b goes to infinity. So the picture here is kind of a little bit different, but, well, the same but different. A is some fixed point. We can think of it as being 1 or whatever. We've got our function f. Maybe it's something relatively manageable, like 1 over x squared or whatever. We've got a point b, which we visualize as being out to the right of a. We can calculate a definite integral from a to b of f of x. And that's something that we know how to do. And hopefully for a particular example, f, we know how to do it. And if we don't specify a value for b, but just imagine it as being some point out to the right of a, the result of that process will be an expression involving b. And then we can imagine b sort of traveling further out to the right, even as far as infinity, and we can take a limit of that expression as b approaches infinity. And we might be able to evaluate that, or we might be able to determine that it goes to infinity. Okay, and that's how we attempt to calculate an improper integral of this type. So we can sort of look at that limit. We can hopefully determine whether it exists or not. If it exists, and if it's got a finite value, then we say that the improper integral is convergent. if the limit doesn't exist, because the value either oscillates between different things or goes up to infinity, then we say that the improper integral is divergent. And there's a version of this as well for a region that goes from minus infinity to some a, which is just noted there. So that's sort of how that's the sort of technical machinery that we use to deal with these problems. Please shout if you have a question or throw the question into the chat. Maybe a practical example at this point would be better than sort of theorizing about rotation and stuff. So here's an example. So the problem is presented to us is to show that the improper integral from 1 to infinity of 1 over x is divergent, which is what just about half of us voted for in the first question there at the poll. So how do we deal with this question? Well, we look at an improper integral. Sorry, we look at an integral from 1 to b of 1 over x. 1 over x is kind of a mysterious function. It's got lots of really special properties, even though it's sort of everyday kind of thing. And we can write down an antiderivative for 1 over x. And of course, unlike all the other powers of x, 1 over x has a sort of special antiderivative. Its antiderivative is the natural log function. So the definite integral from 1 to b of 1 over x is log x evaluated at b and at 1. So what I've written down here is exactly what's written already in the slide. If we take an indefinite integral of 1 over x from 1 to b, and picture the function here, y equals, oops, that's not what I meant to do. Picture the function y equals 1 over x. Graph looks like this. The y-axis is there, the x-axis is here. Picture b temporarily as being some fixed point. 1 is here. And so we're talking about that region, which is, a proper definite integral. Okay, and when we figure out what that is, we get log x evaluated at b and at 1. So we get log of b minus log of 1. Log of 1 is 0, because e to the 0 is 1. And so this is just log of b. Okay, so that's kind of saying, that's already interesting. That's saying, that if we take the area under the graph of 1 over x from 1 to 5, the value of that thing is the natural log of 5. If we take it from 1 to 10, it's the natural log of 10. So already that's quite a cute thing, that the areas under this graph indicated in that green picture there are just the logs, the natural logs of the various positive real numbers. But our question really is, well, what happens to that when b goes to infinity? And the answer, of course, is that, well, when b goes to infinity, log of b goes to infinity as well. So the limit of log b as b goes to infinity is infinite. So, as log b goes to infinity, as b goes to infinity, that's telling us that the area of that entire region to the right of 1 under the graph y equals 1 over x is infinite. Okay, so, and I mean, how you sort of conceptualize this is another kind of almost philosophical question. It means that you couldn't somehow sort of repackage that area and fit it into a finite rectangle. If you were to sort of break up the region and try to somehow, pack it into some finite box, you couldn't do it. It would never fit into any finite rectangle, no matter how big the rectangle was. Okay, so that area is actually an infinite area. The other remark about it, I suppose, is that the function y equals 1 over x it decreases and it approaches 0, but sort of slow enough that the area enclosed under the graph is still infinite. The log function, so the graph, maybe I'll insert a page here. If this isn't useful to you, just feel free to ignore it. It's relevant to the next example. Sort of, if we know that the integral from 1 to b, we're saying here that the integral from 1 to b of 1 over x dx is log of b minus log of 1, so it's log of b. And we're saying here, well, as b goes to infinity, log of b goes to infinity, which is certainly true. But if we think about log, the log function, it's kind of, it goes to infinity, but really slowly. And this is something I think that's kind of worth just kind of reflecting on. The graph of log looks like this, like it's the reflection in the line y equals x of the graph of the exponential function. So it looks like that. And so this is the graph y equals log x, which is the derivative of 1 over x. Okay, so, or sorry. And so it passes through the point 1, 0, of course. And it grows to infinity, but sort of really, really slowly. So slowly that if you think about the tangent lines, the derivative of log x is 1 over x. So if you think about the tangent line to that graph at any given point, like it's 1 over the x value there. And when you travel further out, the tangent line is 1 over x again. So the slopes of these tangent lines are the values of 1 over x, as x labels the points on the x-axis. So the slope of the tangent line is heading towards 0 as 1 over x as we travel out along the positive axis. And what that means really is that, the further out we travel, the closer that tangent line becomes to being horizontal. So the closer this log function becomes to being just a constant function, which would obviously have a horizontal tangent line everywhere. So this function, log x, it grows to infinity, but sort of so slowly that its tangent line is kind of approaching a constant sort of the whole time. It never actually becomes 0. The derivative is always positive, but approaching 0 really fast. So the log x function approaches 0 sort of really, really, really slowly. It's the slope of it grows to infinity. The value of log goes to infinity really slowly. And one way of sort of kind of capturing that is to notice that the slope of the tangent line to the graph y equals log x at various points is actually kind of approaching a horizontal line. So the thing is, it's growing to infinity, but sort of so slowly that the further out you go, the more it resembles a constant function. And so for log b here, which was our integral from 1 to b of 1 over x, yeah, it's going to infinity, but sort of somehow like just about kind of manages to keep growing to infinity. And that's relevant when we look at the next example, which is the improper integral of 1 over x squared from 1 to infinity. So yeah, so this picture is supposed to kind of indicate how the slopes of the tangent line to the 1 over x, to the log function as we travel out, kind of sort of approach horizontal lines. Okay, so yeah, the log function grows to infinity, but really slowly is the key point there. Does anyone have a comment or a question at this stage? Okay, so if not, then let's look at the same sort of technique applied to the next example, which is 1 over x squared. So here the setup is exactly the same. The problem is 1 over x squared instead of 1 over x. So we noted earlier that on the region from 1 to infinity, 1 over x squared sits below 1 over x. So like its height is even lower. It's the domain over which we're integrating from 1 to infinity maybe is very similar, but it's even lower. So, even though the area enclosed under the function 1 over x was infinite, could it be that this one could be finite? So what we have here is a slightly different version of the question, just to include an example where we're working over this, like the negative side instead of the positive side. But if we look at the graph of 1 over x squared over the whole real line, it's an even function. 1 over x squared is the same as 1 over minus x squared. So the graph of 1 over x squared looks like this. Here we're talking about the integral from minus infinity to minus 2, which is the same thing. It's really talking about the integral from 2 to infinity. And that it'll be finite if the integral from 1 to infinity is finite. So, we really care about the behavior at the infinity end of the picture rather than at the place where we choose to start. So here the question, just for the sake of including an example where we're going to minus infinity instead of plus infinity, is integrated from minus 2 to infinity to minus infinity, this thing. So we're talking about the area of this kind of piece of the graph, under this piece of the graph, from minus infinity to minus 2. Okay, the technique's the same. So we can't integrate directly from minus infinity to minus 2, but we can imagine some point here, b, some negative number b out to the left of minus 2. And we can ask ourselves, well, if we were to take the integral from b to minus 2 of 1 over x squared, and then take a limit of that as b goes to minus infinity, would we be able to put a value for what we get? So technique is exactly the same. The actual antiderivative is a bit different, of course, because 1 over x squared is x to the power minus 2. From b to minus 2, this is integral from b to minus 2. So think of b as being some big negative number here. So it's far away from minus 2 out to the left. This is integral of x to the minus 2 dx. And that, of course, integrate x to the minus 2. That's like an ordinary power of x problem. Raise the power by 1 and divide by the new power. So divide by minus 1 or multiply by a negative sign. So this is minus 1 over x at minus 2 and at b. And so we can, so this, which is where this there's a couple of steps skipped there. So, and of course, when we plug minus 2 in there, instead of x, we get minus 1 over minus 2, which is plus a half. And from that, we're subtracting minus 1 over b. So we get 1/2 plus 1 over b. That is the integral from any b out to the left of minus 2 to minus 2 of 1 over x squared dx, or equivalently, integral from 2 to b if you're on the 2 to minus b if you're on the positive side. So what that's telling us is that if b is here, and we're looking at this region, the area of that region between b and minus 2 is 1/2 plus 1 over b, which is 1/2 plus a very small negative number. So it's a bit less than 1/2. Okay. And then if you want to actually go from minus infinity to minus 2, we have to ask ourselves, what happens to that expression when b goes to minus infinity? Okay. And we're looking at b being a negative number heading out to minus infinity. Well, when b is going to minus infinity, this 1 over b is becoming a tinier negative number, so it's going to 0. Okay, so the 1 over b goes to 0 as b goes to minus infinity, or indeed to plus infinity. It's just 1 over a very huge number. And what we find is that the limit of that expression then, 1/2 plus 1 over b, is 1/2. The 1 over b part is going to 0. It's a tiny bit that's been subtracted off 1/2 for any finite version of this. But when we take the limit, as b goes to minus infinity, this 1 over b part is going to 0, and we just get 1/2. And so the conclusion then is that the improper integral from 1 over x squared, from minus infinity to minus 2, is 1/2, that the area of that entire kind of infinite tail of that whole region is actually 1/2. It's finite, and somehow this is like not something you can obviously do physically. That area could be squashed and repackaged into a box of size of area 1/2, like a rectangular box of width 1 and height 1/2 or whatever. And so also, of course, because by the symmetry of the picture, we can note, and the calculation is exactly the same basically, that the integral from 2 to infinity of 1 over x squared dx would also be 1/2. Okay, and you can sort of recognize that from the symmetry of the picture, or you can do the relevant calculation. So yeah, so that's sort of telling us that, yeah, weirdly, these regions, even though they're infinite in extent, their heights can kind of decrease to 0 fast enough that they actually enclose a finite area. And there's, there's nothing unreasonable here in what we've done. We've sort of calculated the finite version of it with a imagined fixed left-hand endpoint, and we've allowed that left-hand endpoint to travel out to minus infinity and looked at what happened to the expression. And in this version, this example, we find that we do get a finite answer, 1/2. And so if you look at other powers of x, so 1 over x, we just realized 1 over x itself would enclose an infinite area to the right of 1 or to the right of any particular fixed point that you might start with. 1 over x squared encloses a finite area. And this relates to the comments of the last very scrawled picture about how slowly the log function grows, or kind of equivalently, how slowly the values of 1 over x approach 0 compared to, for example, 1 over x squared. So essentially, the values of 1 over x approach 0 slowly enough that the area enclosed to the right of 1 under its graph is infinite. The values of 1 over x squared approach 0 faster, and fast enough that that corresponding area is actually finite. So even though these pictures look sort of qualitatively similar to the same sort of shape of region, they're not really the same. They're different enough that one of them actually has finite area and the other one has infinite area. And so if you take as a denominator here anything greater than 1, so 1.1 even, or 1.01 or 2 or 3, you will find that the area here is finite. If you take anything less than or up to 1, so 1 over area enclosed under 1 over x to the 1/2, for example, to the right of 1, that would be greater than the area enclosed under 1 over x, so it would be infinite. So the 1 over x example is just kind of on the cusp of being infinite or finite, which relates to the comments earlier about the log function growing to infinity, but really, really slowly. And so when people work in calculus and analysis, they want to kind of get a handle on these things. Things are sort of growing or converging or approaching limits, but you kind of care about how fast that's happening and what the impact of that is on questions like these area questions. And we'll be looking at that a bit more, and about concepts of convergence as we proceed. So we would say that in this example, you could say, if you wanted to use the kind of official language that the improper integral from minus infinity to minus 2, let's say, of 1 over x squared is convergent and its value is 1/2. Okay, so and the word convergence there relates to other concepts of convergence, like convergence of sequences that we'll see a bit later in the course. So I think the reason why this word terms convergent and divergent are used here to describe the situations where the area is finite and where it isn't. It's not so obvious when you sort of think of the ordinary English usage of the words convergence and divergence, why these words are used here. But I think that will become a bit more natural when we talk about convergence of sequences, which is related and which is where it does make kind of more sense in terms of the usual everyday language usages of these words. Okay, so we're not going to really look at any examples of improper integrals that are sort of worse than this or a whole lot more complicated. The point here is really kind of more about the concept of thinking about these regions that are kind of infinite in one direction and getting infinitely sort of narrow in the other one, and the fact that their areas can sometimes be finite. There is one other type of improper integral that I want to just mention, which is sort of less important for us, but can arise. And here a remark, I suppose, is if we look at this picture, this one, which is indeed a bit of a mess, but if you were to attempt to talk about the improper integral from minus infinity to 2 instead of minus infinity to minus 2, there's another problem there. So, you know, if you were to think about, if you were to think about, where will I put this? I'll put it over here as a little kind of question. Suppose you were to think about integral from, this pen is not working. Oh, there we go. Integral from minus infinity to plus 2, let's say, of 1 over x squared dx. So when you glance at that, it looks the very same as the previous example. But there's a problem. And the problem is all this stuff in here, where we've got a vertical asymptote within that region, as well as all the other behavior towards minus infinity of the function. So this vertical asymptote here, for the values of the function blow up to infinity at 0, is a little bit of an issue if you were to think about that integral that's written there in white. And you might not even notice it. And if you didn't notice it and you just proceeded with the calculation, you'd probably get an answer that might not quite make sense. And that's just the last thing I want to mention. It's more to highlight a potential pitfall than it is really to worry about these examples. So, okay, I'll move on. So another type of improper integral. So if you have a function which has a vertical asymptote for a value of x at some point in the region that you want to integrate over. So here we're talking about the integral from c to d of some function f of x, and here think about c and d as being, you know, just fixed numbers. If there's a region in the interior of the interval from c to d, a point in the interior there where the function actually has a vertical asymptote. So for example, if it's 1 over x and your region includes 0, then you potentially have a problem because the values of the function are sort of undefined at the point where the asymptote is itself, and they're blowing up to infinity to the left and right of it most usually. And potentially this integral also can't be defined. Okay, so for example, if the vertical asymptote is at the left endpoint c, the way we would deal with this would be exactly as we did before, to replace the c there with some point b to the right of c, and look at a limit of this expression as b approaches c from above. Similarly, if you had a vertical asymptote at the right-hand limit point, you take an integral instead from c to b, where b is something between c and d, and look at the limit of that as b approaches infinity from below. If the vertical asymptote is at some point in the interior of the interval that you're integrating over, let's say at some point m, you'd rewrite it as the integral from c to m plus the integral from m to c, and deal with both of those according to the previous kind of advice. So this is kind of how we deal with these things. I think this probably makes more sense after we look at an example. So let's look at an example. Supposing you were presented with the problem of deciding whether this improper integral from minus 2 to 4 of 1 over x squared is convergent or divergent. So the first question you might ask yourself is, well, say, you know, what's wrong with that? What's improper about it? Well, what's improper about it is that 1 over x squared is not defined at 0, and 0 is in between minus 2 and 4. So the picture's like this. The function y equals 1 over x squared is like this. it has this problem at 0 and around 0. And we would have to bear that in mind if we're trying to think about whether this integral exists or not. So it just like before, the picture's not the same, but it's analogous. Oops, sorry, this thing keeps jumping around. If you were to think about the area between -2 and 0 under the graph 1 over x squared, well, it's not infinite in width, but it is infinite in height. 1 over x squared is a vertical asymptote there. Or 0 is there's a vertical asymptote at 0. The value of 1 over x squared is not defined at 0, but it's defined everywhere to the left of 0. So that area potentially could be finite or it could be infinite. It's another one of these things where it's like it's infinitely high, but it's got widths that approaches 0 as you travel up. Okay, so can we figure out whether that is a finite or an infinite area? So the strategy here would be to think about the integral that we have to calculate, which is from -2 to 4, split it up into the integral from -2 to 0, which is where the problem is, plus the integral from 0 to 4. Okay, if this thing is something that we can make sense of, then it'll be the sum of those two things, and we'll have to be able to make sense of both of those separately. And to look at the first of them, when we're talking about integration from -2 to 0, 1 over x squared, the issue there is that there's a vertical asymptote of this function. Its values blow up to infinity as we approach 0. And so the strategy for dealing with it would be to instead take integral from -2 to b, where we think of b as being a bit to the left of 0. Okay, that's fine. We can deal with that for any b that's not actually 0. To the left of b, we can do that. So we'd look at the integral from -2 to b of 1 over x squared. Antiderivative for 1 over x squared is -1 over x. So we'd be talking about -1 over x evaluated at b, which is here to the left of 0, to the right of -2. Plug in the b there, we get -1 over b minus -1 over 2. So this is what we're dealing with. But now, rather than looking at a limit as b is going to infinity, we're looking at the limit of this thing as b is approaching 0 from the left, but it doesn't matter. So when b is approaching 0, 1 over b is getting very big. It's 1 over some tiny thing. So when b is approaching 0, this thing, -1 over b, is approaching, well, b is approaching 0 from the left, so it's negative. So 1 over b is approaching infinity, plus infinity, but it doesn't matter whether it's plus or minus infinity. It's blowing up. This limit doesn't exist, okay? The limit as b goes to 0 of 1 over b or -1 over b doesn't exist. It blows up to infinity. And that's telling us that the area of that region that's shaded here in green is infinite. It really is infinite. It can't be repackaged into any kind of finite box. Okay, so this improper integral from 0 to from -2 to 0 of 1 over x squared, it's improper sort of in the vertical direction instead of the horizontal direction that we saw before, doesn't exist. The conclusion then is that the improper integral from -2 to 0 of 1 over x squared dx diverges. It's an infinite area. And that means it doesn't even, we don't have to look at even at the second part of it, which was this part from 0 to 4, although that also will diverge, but we don't even care at this stage. Once the first one is divergent, it tells us that the entire improper integral is divergent. We can't attach a value to it. So the answer there would be that the improper integral is divergent. These examples, I would say, are, for us anyway, at the moment, kind of less critical than the first type, the ones where it's the region over the x-axis that's infinite. But a remark and a sort of note of caution there is, this is exactly the sort of thing that I might hit you with in a homework sheet or an example. And if you just answer that problem, you could easily not notice if there's anything weird about it. It just looks like an ordinary definite integral exercise. You might just integrate, plug in the values 4 and -2, and you get the answer -3/4, and you might not take any notice. You might say, okay, there's the answer. But it would be wrong because it wouldn't have taken into account the fact that we have this asymptote in the region from -2 to 4. Okay, so I suppose this technique, the one we've been applying, is generally reliable, but we have to be aware of the risk that somehow inside our regions there could be vertical asymptotes. So, I mean, I won't deliberately try to catch you out with anything like that, but we should be aware of it when we're thinking in general about integration problems, because, we're kind of applying this method is fine as long as the function is sort of well behaved within the region that you're talking about. Okay, that's it for today. I'm sorry, I've cut it fine in terms of time. Apologies for that. Thanks to everybody who joined us for the recording. I'm going to stop the recording now and see you all tomorrow. Thanks a lot.